Hello, once again, a great welcome to this series on machine foundations. Yes, we are making a lot of progress. That's a good news. And this is lecture 3, and it is all about the free vibrations undamped. So, if you remember in our last video, I explained very clearly the different terms used in the vibration theory, wherein we explained the meaning of the term undamped free vibrations, wherein we know that an external force is not required to initiate the vibration. Instead, we require an initial displacement or a velocity or both to start a free vibration. So let us get into the mathematical theory of free vibrations that will obviously help us to understand how a system responds under free vibrations with no damping effects. Okay, as usual, this is our spring mass model that is used to analyze the response of the free vibration. It's a general classic spring mass model, and we know from our earlier discussion that the dynamic equation of equilibrium for the SDOIF can be represented through the equation m into u double dot plus cu dot plus ku is equal to ft. Obviously, we know that this is the general equation of dynamic equilibrium, and for a case of a free undamped vibration, we know that we don't have any exciting force. Accordingly, Ft equal to 0, and we are talking about an undamped vibration wherein there is no damper element, that is, the value of C will be set equal to 0. So if we make this substitution, the general dynamic equation of equilibrium will reduce to a simple equation, that is m into u double dot plus ku equal to 0, because we don't have a term c into u dot, and ft is also 0. So now we are going to analyze this simple linear homogeneous differential equation in order to obtain the response of the system. Remember here, the system parameters are the mass m and the stiffness k, and we would like to obtain what would be the response of the system u at any time ut. Okay, fine. So if we normalize the earlier equation, which is m into u double dot plus ku equal to 0, with mass m, we have u double dot plus k by m into u equal to 0. So we simply divided every term with a mass m. Now we are going to make a substitution. That is, we are going to define a new term omega n. Let omega n is equal to square root of k by m. We will understand, or I will explain, the importance associated with the term omega n, and then I will provide a definition of this term. So for now, it's a simple substitution for square root of k by m term, which is omega n. So if I make this substitution, this equation will reduce to u double dot plus omega n square into u equal to 0. And remember, we want to find out the response of the system u at any time t, that is ut. So now let us assume that the general solution u takes the form u equal to a into e raised to st. If we assume u equal to a into e raised to st, obviously the first and the second derivatives will provide us the velocities and the acceleration at a time t, which means the velocity is given by u dot is equal to a into s into e raised to st, and u double dot, that's the acceleration, is given by u double dot is equal to a into s square into e raised to st. Now, if we substitute the values of u double dot and u in the equation u double dot plus omega n square u equal to 0, we obtain the characteristic equation in S, that is s square plus omega n square equal to 0. And that provide us obviously two values for s. That is s is equal to plus or minus omega n into square root of minus 1. Obviously, we know that square root of minus 1 is the imaginary number denoted by I, which means that s is given by s is equal to plus or minus omega n into I. This means that the general solution can be represented through u equal to a1 into e raised to s1t plus a2 into e raised to s2t. Because remember, our response, that's a vibration analysis problem, has two initial conditions relevant to the velocity as well as the displacement. So this means that substituting s1 equal to plus omega n into I and s2 equal to minus omega n into I provides us the general solution of the form u equal to a1 into e raised to I into omega nt plus a2 into e raised to minus I omega n into t. Obviously, using our basics in mathematics, we know that this exponential function e raised to I omega nt is nothing but cos omega nt plus I sin omega nt, and e raised to minus I omega nt can be written as cos omega nt minus I sin omega n into t, which means that the displacement now u takes the form u equal to a1 into cos omega nt plus I into sin omega nt plus of a2 into cos omega nt minus I into sin omega nt, which can be simplified to u is equal to a1 plus a2 into cos omega nt plus I into a1 minus a2 into sin omega n into t, which means that we have two constants a1 and a2 which can be readily evaluated using the initial conditions. Now let us substitute the initial conditions, that is at a time t equal to 0, the displacement u is equal to u0. And again at time t equal to 0, the velocity u dot is v0. Now substituting these initial conditions at a time t equal to 0 and evaluating a1 and a2, we can write down the response of the undamped free vibration ut as u0 into cos omega nt plus v0 by omega n into sine of omega nt. Looking into this equation, we can say that we have the initial conditions, that's the initial displacement u0 and v0, and also we have one important parameter omega n, which decides the response ut. Now let us get a little bit more detail into this term. Now if we look into this general response, ut is equal to u0 into cos omega nt plus v0 by omega n into sine omega nt, it's very easy to see that the displacement ut is a harmonic and therefore it is periodic. What does it mean? It does mean that u can also be represented either by a sine or a cosine function of the same frequency, which means that here omega n represents the frequency of the response function ut, right? So what is omega n? Omega n is the natural frequency square root of k by m. This is what we have defined in the earlier slide. Let omega n is equal to square root of k by m. Now we find that omega is such an important term. It is nothing but it is the natural frequency of the system, which provides how many radians per second of the response ut. Now, once we have the natural frequency in radians per second, it can be expressed comfortably in cycles per second, or popularly known as hertz. How do you do it? Simple. That is f is equal to 1 by 2 pi into omega n. That is, omega n, we know it is radians per second. If you divide it by 2 pi, we obtain in cycles per second or hertz. So we have the natural frequency in hertz as f equal to 1 by 2 pi into square root of k by m. And what is natural period t? The natural period t is 1 by f, which is nothing but the time required to complete one cycle. Now let us graphically visualize this response. So the response as expected is a harmonic. Again, it is a periodic motion. And here, as you can see that at a time t equal to 0, along the x-axis, we have the time t, and along the y-axis is the displacement or the response of the system measured from the equilibrium position. And we see that at a time t equal to 0, we have the displacement u0. And if I draw a tangent to this response curve at t equal to 0, obviously we know that it is the slope the tangent makes with the horizontal is the velocity, because we know that the velocity is du by dt. So this is what is being marked over here as the initial velocity v0. And as you can see that the system undergoes a periodic motion, and the system has got a natural period Tn. What was the natural period Tn? It is nothing but the time required for the system to complete one cycle of motion, that is from A, B, C to E. This is what is clearly marked over here. The natural period of the system is equal to 2 pi by omega n. Remember here that the amplitude of the vibration, it remains constant. That is, once the system is given in initial displacement, it goes on vibrating without any decay, without any reduction in the amplitude. And we find that even at t equal to infinity, the amplitude remains a constant. Obviously, we know that such a system is very difficult to exist in practice, but this will always help us in order to further proceed into the damped vibration systems. So this is how you should interpret the equation of motion. That is, the equation of motion ut, it consists of an important parameter of the system omega n, which we call as the natural frequency of the system. And this natural frequency of the system reflects the system properties, important properties, stiffness as well as the mass m. And we also conclude that the motion is periodic and the frequency is omega n, and the time required for the response to complete one perfect cycle of vibration is the natural period capital T. Now, in order to make our explanations or the mathematical derivation much more simpler, or in order to get a little bit more deeper understanding, what I did is I have taken a very simple problem. So look here. Here I have considered a simple spring mass system wherein the spring is represented through the stiffness K is equal to 100 Newton per meter and the mass m equal to 10 kg. So here I am going to provide you two cases. In case 1, this system is given an initial displacement u0 of 20 millimeters but no velocity. And the system is given an initial displacement and then just released. We would like to know what will be the response under case 1. Case 2 is a little bit more different. In addition to the initial displacement u0 of 20 mm, I have also imposed an initial velocity v0 of 50 millimeter per second. So obviously we know that the first step involved will be the computation of the natural frequency in radians per second, the frequency calculation in hertz, and also the natural period capital T. Look here. Now if you substitute the value of k and m, the natural frequency omega will be calculated as omega n is equal to 3.16 radians per second. And this can be converted easily into the frequency in hertz just by dividing this by 2 pi. This is what is written over here, f equal to 1 by 2 pi into omega n. So which means that f equal to 0.503 hertz. It means that the system makes approximately 0.5 cycles per second. And now the natural frequency is very simple. The natural period capital T, it is 1 by of the frequency, and that is 1 by of 0.503. That is equal to 1.99, which means that this spring mass system with K equal to 100 Newton per meter and M equal to 10 kg requires a time of 1.99 second, approximately 2 seconds, let us say, to complete one cycle of vibration. Now let me just provide you the response plot for both these cases, case 1 and case 2. Look here. Here, as you can see that case 1, here I have represented through a curve in a red color. As you can see that here the initial displacement was 20 millimeter. Yes, at t equal to 0, it is 20 millimeter. And if you draw a tangent at t equal to 0, obviously it is a horizontal, that is the velocity is equal to 0, that is v0 is equal to 0 millimeter per second. And remember, this plot is constructed using the simple equation u equal to u0 into cos omega nt plus v0 by omega into sine of omega t, wherein we have already calculated omega. We have for case 1 and case 2 different initial conditions u0 and v0. So look here. So coming to case 1, as you can see that the motion is periodic, and we can say that the system takes how much time. For example, at this point the time was 0.5, and when it complete one cycle the time is approximately 2.5. That means the difference is 2.5 minus 0.5, that is a 2. This is nothing but our t equal to 1.99 second. Now again I have taken another case wherein I change the initial conditions slightly. I kept the initial displacement u0 approximately the same, but I also imposed an initial velocity v0 which is 50 millimeter per second, and the resulting response is indicated by the curve in green. And remember, what you need to do is you just put the u0 and v0 values into this equation. You obtain this curve that is marked in green. As you can see that here again the displacement is 20 mm, but you will find that here the graph is an ascending one. It has got a slope at time t equal to 0, which if you measure and calculate, you will find that is 50 millimeter per second. Further again, you will find that the curve in green also has got the same natural period. For example, if you take at this point, this is approximately say 0.75, and if you take here, this is approximately 2.75, which means that again the time period, that's a period required for one cycle of vibration, is again approximately 2 seconds. So that's all about the response of the it's an undamped free vibration. And remember here 3 things. That is number 1, the response continues, that is the amplitude of vibrations do not decay with the time because it's an undamped system. Second, the system has an important parameter known as the natural frequency omega n, calculated as square root of k by m. K is the stiffness, m is the mass. And remember, t is the natural period of the system, which means the time required to complete one cycle of vibration. So I think that's all about this small introduction on undamped free vibration. And in the next lecture, we'll again consider a free vibration but under damping. And once that lecture is over, you will be in a position to exactly compare the influence of the damping on the free vibration systems. Okay, fine, that's all. So thanks a lot for listening.